DDR1, Double Data Rate SDRAM. DDR1 was the first generation of DDR memory, introduced around the year 2000. Before DDR1, computers used SDRAM, which could transfer data once per clock cycle. DDR1 changed this by allowing data to be transferred twice per clock cycle, once on the rising edge of the clock and once on the falling edge. This is where the name double data rate comes from. Internally, DDR1 used a 2-bit prefetch buffer. This means the memory would fetch 2 bits of data at a time from the memory cells and then send them out efficiently. However, DDR1 had several limitations: high operating voltage of 2.5 volts, very low memory bandwidth by today's standards, small memory capacities. Produced more heat. DDR1 was a major improvement over SDRAM, but as CPUs became faster, DDR1 could not supply data quickly enough. That led to the next generation, DDR2, improving bandwidth and efficiency. DDR2 was not simply faster DDR1. Its main goal was better efficiency and higher bandwidth. The biggest internal change was the prefetch buffer. DDR1 used a 2-bit prefetch. DDR2 increased this to a 4-bit prefetch. This means DDR2 could prepare twice as much data internally before sending it to the CPU. Even though the internal memory core did not run much faster, the output data rate increased significantly. DDR2 also reduced voltage, from 2.5V in DDR1 down to 1.8. In DDR2, this resulted in lower power consumption, less heat, better stability. However, DDR2 introduced a trade-off. Because it focused on bandwidth, latency increased. Early DDR2 modules often felt slower in real-world tasks compared to DDR1 at similar speeds. Still, DDR2 was an important step because it proved that memory performance is not just about clock speed, but about how much data can be moved efficiently. DDR3, balancing speed, latency, and power. DDR3 is where memory technology became truly balanced. DDR3 doubled the prefetch buffer again, from 4-bit in DDR2 to 8-bit prefetch in DDR3. This allowed DDR3 to move much more data per memory access. DDR3 also improved voltage efficiency. Standard DDR3 ran at 1.5 volts. Low-voltage DDR3L ran at 1.35 volts. This made DDR3 especially good for laptops' long workloads, energy-efficient systems. Compared to DDR2, bandwidth increased significantly. Latency improved. Power consumption dropped. This balance is the reason DDR3 stayed mainstream for many years. DDR3 was fast enough that CPUs did not outgrow it quickly, and it became one of the most stable and widely used RAM generations ever. DDR4, higher capacity and modern scalability. DDR4 focused less on raw speed and more on capacity, efficiency, and scalability. Interestingly, DDR4 kept the same 8-bit prefetch buffer as DDR3. Instead of increasing prefetch, DDR4 improved the internal memory organization. Key improvements in DDR4: higher memory density, larger RAM modules, better bank management, improved data access patterns, voltage was reduced again, DDR3 to 1.5V, DDR4 to 1.2V. This significantly reduced power usage, especially in systems with large amounts of RAM. One important concept to explain with DDR4 is latency numbers. DDR4 often shows higher CAS latency values, but this does not mean it is slower. Because DDR4 runs at much higher speeds, the actual time delay is often similar or better than DDR3. DDR4 became the standard for gaming PCs, workstations, general-purpose computers, and it remains very popular because it offers excellent performance at a reasonable cost. DDR5. A new memory architecture. DDR5 is not just an upgrade, it is a redesign of how RAM works. The most important change in DDR5 is memory channels. DDR4, 164-bit memory channel per RAM stick. DDR5, 2 independent 32-bit channels per S stick. This means one DDR5 stick can handle 2 data streams at the same time, improving efficiency and reducing bottlenecks. Another major change is power management. In older DDR generations, power was managed by the motherboard. In DDR5, power management is moved onto the RAM module itself using a chip called a PMIC. This allows more stable voltage control, higher achievable speeds, better power efficiency. DDR5 also dramatically increases bandwidth. It is designed for workloads like content creation, AI processing, heavy multitasking. Future CPUs. DDR5 supports much larger memory capacities per STIC, making it ideal for high-end systems. However, DDR5 currently has drawbacks: higher cost, higher latency compared to mature DDR4. Many applications do not yet fully utilize its bandwidth. This means DDR5 is future-focused, not always faster in today's everyday tasks. Direct comparison summary. DDR1, DDR2, bandwidth increased, power reduced, latency increased. DDR2, DDR3, better balance of speed, latency, and efficiency. DDR3, DDR4, higher capacity, lower voltage, improved stability. DDR4, DDR5, architectural redesign, parallel channels, future scalability.